Friedel Crafts. It is an example of electrophilic, aromatic substitution. The reason why it's called that is because you take an aromatic and an electrophilic molecule and you end up doing a substitution reaction. So I will draw a aromatic molecule. This is benzene. This is aniline. It is an aromatic. An electrophile, let's react it with, we'll just do a regular acylation. We'll react it with acyl chloride. I forgot to draw a bond. With acyl chloride. And all of these Friedel Crafts are going to require a Lewis acid catalyst. We're using aluminum trichloride. This halogen should match this halogen. So if I used acyl bromide, I'd have to use aluminum bromide because. Mechanism. Actually, let's just show what the overall reaction is. You will, one, mess up your pen for the 1000th damn time. You're going to end up adding the acyl group opposite or para to your electron donating group, your EDG, for reasons that are not covered in this mechanism, so let's continue on. The first thing you have to do is prepare your electrophile. This is already electrophilic, it's super delta plus, but we can make it even more electrophilic with the help of a catalyst. Here is our catalyst. Aluminum's got a juicy empty orbital there. It's a Lewis acid. It wants some electron density. And you know what? Acyl chloride has just what it wants. These two electrons are going to hop in over here. You can draw it from the bond to the Lewis acid, or you can draw it from the bond onto the chlorine, onto the Lewis acid, the exact same thing. You're going to get AlCl4. This gained electrons is going to gain a minus charge, plus this guy right here, which looks a little weird. It's called an oxonium cation. But it's okay, he's not going to last for very long, because now when we have our aniline, I'll put the NH2 down here so it's closer to the electrophile. Electrophile, aromatic, now let's do a substitution. These two electrons right here is going to be a nucleophile to our electrophile. We will turn the molecule. No, we won't. It's fine. We don't have to turn it. This pi bond did not change. This pi bond did not change. We made a bond here. Because we made a bond right here, that means we lost electrons right here. So we have a positive charge. Our negative charge, remember, is still up here. It is our AlCl4 minus at the time. We broke aromaticity. We need to reform it. And because this is a catalyst, we know that we have to regenerate AlCl3 at some point. So I'm going to draw a arrow from the AlCl bond electrons to this hydrogen right here. These two electrons are going to come back down, reform the pi bond, and restore the aromaticity. That gives us our final product of para-amino acyl something. Plus your original catalyst. It is regenerated. It's a catalyst. You could add any electrophile, really, para to your electron donating group. Instead of, let's say, instead of the acyl chloride, I had something like CH3Cl. I can do the exact same mechanism, and I would just add a methyl group across from it. This is another way, to generate carbon-carbon bonds through aromatic electrophilic substitution. So if you need to add something to a benzene, this is probably the way that you're going to go.